As we begin to talk about systems with more than one phase and more than one component or more than one chemically distinct species, the concept of chemical potential will become very important. So let's take a look at what chemical potential is. The chemical potential is most easily understood in terms of the Gibbs free energy of a system. If the individual components in the system do not interact with each other in any way, then the amount of Gibbs free energy due to the pure system is simply additive to give the total Gibbs free energy for the system. If we look at the Gibbs free energy per mole of one of the components and multiply by the number of moles of that component in our mixture and add that to the number of moles times the molar Gibbs free energy for the next component and so forth and so on, we should get the total Gibbs free energy of the system, because when we mix these, there's no extra interactions, potential energy of interactions over what is already existing in the pure systems. When there is an interaction energy between particles, this strategy will not work because each particle contributes a certain amount of interaction energy depending on the average environment that it is in. Because the interactions occur between dissimilar molecules, I have to figure out how much I'm going to attribute to each of the different types of molecules if I want to split the Gibbs free energy up into an amount due to each of the components in the system. This is what the chemical potential does. It splits up the Gibbs free energy, the total Gibbs free energy, into an amount due to each component in the system. We can think about how much of each of the different interaction energies to attribute to each of the types of molecules involved in that pairwise interaction by looking at the total Gibbs free energy as I change the amount of one of the components in my system. I'll keep the temperature, the pressure, and the number of moles of all the other components, not equal to the component I'm interested in, constant. Therefore, I'm looking at the amount of Gibbs free energy that's due to just simply one of those components. This is the formal definition of the chemical potential of a given component. The chemical potential is important because it allows us to link one substance at the start of a transformation to another substance at the end of the transformation. That is because the amount and chemical potential of each of the components in the system are linked to the total Gibbs free energy. If I change one of those components, the others have to change in a fashion consistent with the change in the total Gibbs free energy. So all of these components are linked together through the total Gibbs free energy, and therefore we can understand how one component transforms into another component either through a phase change or a chemical reaction. And so the chemical potential is the important concept when we're talking about phase changes or chemical reactions. Since the total Gibbs free energy can be expressed in terms of a sum of the chemical potentials of each of the components, we can write that the change in the Gibbs free energy is equal to the number of moles of component 1 times the change in chemical potential of component 2 plus the chemical potential of component 1 times the change in the number of moles of component 1 plus, and so on, plus the number of moles of component C times the chemical potential, change in chemical potential for component C, plus the chemical potential for component C times the change in the number of moles for component C. Here we've just used the product rule in taking the total differential, where we take the first function times the derivative of the second, plus the second function times the derivative of the first. The total change in Gibbs free energy can also be expressed as minus S dt plus V dP plus mu1 dN1 plus, and so on, plus mu c dNc. Because these are both equally valid expressions for the total differential of the Gibbs free energy, we can equate the two and show that 0 is equal to S dt minus V dP plus N1 d mu1 plus, and so on, plus Nc d mu c. This equation is called the Gibbs-Duhem equation and gives us the link between the chemical potentials of each of the components in the system. Notice that for something like a phase change, where we have constant temperature and pressure, so that dt and dP are both equal to 0, that 0 has to be equal to N1 d mu1 plus, and so on, plus Nc d mu c. So if we look at something like vaporization, where we take a liquid to a gas, then our first component is the liquid, and our last component, the second component, would be the gas. And so we can write that N for the liquid, d mu liquid, plus N for the gas, d mu gas, has to equal 0. So this gives us an equation which allows us to determine the number of moles of liquid and gas in our system. Thus, we have linked the one substance at the beginning of a transformation to the substance at the end of the transformation. And this gives us a way into determining equilibrium amounts of components in a system.